my name is Chad Sockwell, and I'm going to be talking about Hamiltonian structure preserving reduced order modeling for the shallow water equations. Next. So reduced order modeling in general is a data-driven, physically constrained model with the goal to have an inexpensive simulations that are stable over long time spans. And ideally, you get some data from some high-resolution simulations from some sparse parameter sets, such as forcings, viscosities, etc. And you can fill in the gaps with different parameters that weren't seen from the original model with the reduced order model at a cheap expense. And so I have a little flow chart here. Reduced order modeling has two components. The more expensive offline component, which includes running the high fidelity model, building empiric orthogonal functions. And for the type of reduced order modeling I'm doing, you build a very inexpensive physical model in terms of these EOFs, which is opposed to a more statistical model where you would infer one just from the data alone. So this is where the word physically constrained comes in. And then you have the online component, which consists of running this very inexpensive model and performing some applications like you see here. Next. And so once again, I'm going to be using the rotating shallow water equations. I think the first three talks use this. The only important part of this slide is we need the mimetic truss scheme, since it preserves what is known as the Hamiltonian structure. Next. And so I have that written down here, although you saw it in Zhu and Constantine's talk. The main thing I want to point out here is the skew symmetry of this J operator that exists in the shallow water equations. And I'm going to want to try to find a way to maintain the skew symmetry in the reduced order model. And we're going to see why that's important next. So the first step is you run your high fidelity simulation, and which can just be impasse or E3SM, and you get some snapshots, which are just solutions at different times, possibly from different runs with different parameters, and you arrange them in a snapshot matrix, this big Y here, and you can shift and scale them to ensure mass conservation, so that's not an issue. And then you essentially derive empiric orthogonal functions, which include setting up some SVD or eigenvalue problem and finding the R most dominant modes, which can be the eigenvectors or the singular vectors. And so we choose to do this in a special inner product, which we call the energy inner product, generated by a matrix D, which is just the second derivative of the Hamiltonian. And we find that this gives us better accuracy and gives some nice analytical properties as well. And so once you solve this SVD problem in this inner product space, you get this basis phi at the bottom. And you also need this adjoint operator, which is just like the transpose of the modes in the space. Next. And so now that you have your empiric orthogonal functions, which we're going to treat as the basis, as you'll see why that's important here in a second, we want to build this reduced order model. So I have here again this Hamiltonian model, and most conventional ways of building reduced order models have an issue, and then that if you build a reduced order model for a Hamiltonian system, the resulting reduced order model is not Hamiltonian, which means it's not going to conserve energy in the absence of forcing, and this can possibly lead to stability issues and a blow up after a certain time horizon. And so some ideas that have been explored by several people, including our own Zhu Wang here today, is to build a reduced order model that preserves this Hamiltonian structure. And so to do this, I have to make a couple of assumptions. Namely that my solution Y can be represented as a linear combination of the empiric orthogonal functions, which we're going to consider a basis. And I do that by approximating Y by B times some vector A, which gives me that linear combination. And in order to preserve this Hamiltonian structure, I want to further assume that I can represent the first derivative of the Hamiltonian, delta H, by B transpose, which is a projection operator, times the first derivative of the Hamiltonian. And so I plug those assumptions into my model, and then I perform some algebra, and I get a reduced order model. And so now this model operates in terms of the empiric orthogonal functions and in terms of A. So if you have 5 empiric orthogonal functions for your reduced order model, you now went from a model that maybe had millions of degrees of freedom to a model that has 5 degrees of freedom. And so since we made these special assumptions in order to preserve the Hamiltonian structure of the model, I can realize that I have a reduced J operator and a reduced delta H operator that have very similar properties as the original model, and this reduced order model can actually conserve energy in the absence of any forcing. Next. And so to show you that, I ran the energy conserving properties. I ran a very simple test case. So I have the SOMA geometry, and I use a quasi-geostrophic initial condition for 5 days. And I have plotted here the energies for the conventional reduced order model, which is in blue. So this is the one that doesn't conserve energy. And as you can see, after 5 days, this energy starts to grow very quickly, whereas it should be a straight line. And this can possibly lead to an instability and a blow up, and so it's not appropriate for ocean modeling. However, this Hamiltonian structure preserving ROM, the line in the red, gives you a straight line, so therefore it conserves energy, and it hopefully gives you more stability. Next. So now that I think I have stability, my next question is ROM appropriate for more turbulent simulations, such as the SOMA test case, which has lots of eddies in it? And so I ran a SOMA simulation, a single layer one, for 4 years. And I wanted to construct the snapshot matrix, and I looked at the singular values of the snapshot matrix, which are on the top right. And you see the magnitude versus each singular value, and it decreases rather quickly. And so this is telling me most of the energy is contained, or most of the solution is contained in the first few empirical orthogonal functions. And so it looks like I can actually compress the solution in terms of these empirical orthogonal functions. And so just to give you a visualization, on the bottom left, I have the full solution at some time. So this is the velocity vectors, and the magnitude is the density. And on the right, I have the solution projected onto the first 20 empirical orthogonal functions. And so you see that they look almost the same. And so that's a very good sign. Now the question is, can I use this reduced order model to propagate these in time? Next. And so I ran another SOMA test case. This one's only a year long, but this time I'm using the reduced order model. And just so that you know, it has wind forcing, drag, biharmonic smoothing. This is the same test case that Constantine used towards the later part of the slides. And this is on top of a 10-year spin-up. And the time integrator is running a cut of 4. But a nice caveat of reduced order modeling is, since you discard some of these higher order modes, or the empirical orthogonal functions, typically you have a very less restrictive CFL condition that use larger time steps. So I have some results in this table. The first line is the full model using 75% of the max time step for RK4, and you get approximately 2 simulated years per day. And then I have this energy conserving ROM model, the HSP-ROM, with 15 empirical orthogonal functions, 25 and 40. And in all cases, I'm actually using 100 times the original time step of the full order model. And you can see going down for the simulated years per day, I'm getting tremendous speedups. Starting with 5,000 simulated years per day, which is huge, but I have kind of a not so good error. And so as I increase the number of basis functions, the error starts to decrease, and I still have a pretty reasonable speed up at the bottom with 40 basis functions of about 500 times the original model. Next. And so to give you an idea of what the solutions look like for different sets of basis functions, I have the velocity after 1 year for the full model in the top left. On the top right, I have the solution from the reduced order model with 15 basis functions, 25 basis functions on the bottom left, and 40 basis functions on the bottom right. And if you look at this plot on the top left with 15 basis functions, it looks a little bit different from the full order model. But if you look at the ones with 25 and 40 at the bottom, they look almost like the full model, which is on the top left. And so for the last 2 lines, for 25 and 40 basis functions, you're doing pretty good in terms of accuracy. Next. And so in conclusion, I see that I can get stability, good energy conservation properties. I didn't show mass conservation, but it is ensured. And you get significant speed ups, sufficient accuracy, depending on your application. And so in future research, I want to, of course, move to the primitive equations. I'd like to do some predictions across these different parameters, so not just repeating the same parameters I used before, and then apply this to some applications such as UQ or DA, or one problem I'm going to work with Van Rokel is the spin-up problem, or at least attempt it. And there's also some implications in approximating the speed function with this reduced order basis as well.
Okay. So how much time do we have left, Luke?
We have about 2 minutes left for questions, if anybody has it on any of the presentations.
You can send questions either to individuals or to me, and I'll forward them to individuals any way you want after this if you want.
All right, does anybody have any questions?
I'll ask another question if nobody else will, which is just what problems do you foresee moving from the shallow water equations you've mostly used so far to the full model? Yeah.
What difficulties? Yeah,
right.
So there's various algorithms. So for the exponential integrators, it's mainly an issue of combining it with a tracer discretization. So we don't foresee too many difficulties there. But for the localized exponential integrators, we have to go from single layer shallow water to multi-layer shallow water. So this is going to be a challenging task, and this is what we're working on.
Okay. Thanks.
All right. Well, if others have questions, you can contact Max, as he said, and he'll forward them on. Otherwise, I'll thank the speakers and we'll sign off. Thanks, everybody, for joining.
Thanks.
Thank you.